So now let's move on to our third talk on adaptively sparse transformers.
Hello everyone, I'm Gonçalo, and this is joint work done by myself, Vlad Nicolai, and André Martins at the University of Lisbon. So I think it's no surprise to anyone here that transformers are currently one of the best models to get you state-of-the-art results in a certain task. But what did they learn about language? If you try to answer this question, you might find that transformers have a lot of parameters. And sure, attention heads may help you to visualize what's going on inside, but they are completely dense. And what I mean by that is that every output is connected to every input. So even if your input is multiplied by a very small probability, it will affect your output in some way. We think that to better answer the question of what do these models learn about language, our bet is to use sparsity. We think that it helps interpretability, since now the outputs won't be connected to every input because there will be zero probabilities. It helps to discover linguistic structure in the model, and also for efficiency. In this paper, we focus on the first two. So in the transformers, you have all of these multi-head attention mechanisms. And what these do is that they use this softmax normalizing function to get you a probability distribution that will be multiplied by your input representations. These softmaxes can be found in several places. In the self-attention in the encoder, in the self-attention of the decoder, and also in the contextual attention, also in the decoder. Our idea in this paper is to have sparse transformers. And what I mean by that is that we're going to replace that softmax function in all of those attention heads by a sparse normalizing function. Furthermore, since not all heads may benefit from sparsity, we're gonna let the model learn in each of those attention heads how sparse it should be via learnable parameter alpha. Here's some related work that also uses sparse transformer. It's OpenAI sparse transformer, and an earlier work presented earlier this year at ACL, the adaptive span transformer. The main difference between our model and these two models is that we are able to have non-contiguous attention. And what I mean by that is that you can have zero probabilities in between the non-zero probabilities, as you see in the example here. So let's take a step back and look at something that we are all familiar with, which is a softmax function. What it does is just it exponentiates a vector z and normalizes it. It has the property of being fully dense, so every output will be strictly greater than 0. On the other end of the spectrum, we have argmax. And it turns out this is pretty neat. It can be written as this constraint optimization problem of the dot product of your vector z that you want to normalize and the vector p that is constrained to be in the probability simplex. If you solve this optimization problem, your p will be a one-hot vector, where the 1 is in the place of the maximum value of z. This is sometimes used as hard attention, but note that this is not differentiable. You'll have to use something else than gradient descent to be able to train something with argmax. In NeurIPS 2017, Nicolai and Blondel introduced this regularized argmax. It introduces this regularization term to this optimization problem that I just talked to you about. And basically, by taking this regularization term omega to 0, you get argmax, just as in the previous slide. It turns out that when you use instead as a regularization the Shannon entropy in this optimization problem, you retrieve softmax. So if you do this optimization problem with the Shannon entropy as a regularization, your p, the p that you get in the end of the optimization, will be exactly the same as if you would compute softmax over your vector z. Furthermore, if you use, for example, L2 regularization, you'll get sparse-max, which is another normalizing function that is able to get sparse outputs and is differentiable and was introduced in ICML 2016. The question remains is there something in between all of these normalization functions? And there is. We call it alpha and max. It was proposed earlier this year at ACL by our group. And it uses this regularization term, and it's parameterized by an alpha that needs to be greater than 0. And by varying alpha, you get all those different normalization functions that I talked earlier. So when alpha goes to infinity, you get argmax. When alpha equals to 1, you retrieve softmax. When alpha equals to 2, you get sparse-max. And everything in between still works. The key result here is that for any alpha that is greater than 1, your output vector can be sparse. And the propensity for sparsity will increase as you increase alpha. Here's a visualization of that. So here we have alpha equals 1, which is softmax. In the 2D case. And you can see that it never reaches 1 or 0. But as you increase alpha, now you can start having sparse probability distributions. And as you increase it, the propensity for that sparsity also increases. So it will be more probable that you get a very sparse output. The main idea of this paper is to learn this alpha. So in the previous work that I mentioned, this was done in an RNN sequence-to-sequence model with just one attention mechanism. And so my colleagues varied alpha as a hyperparameter. But in a transformer model, you have a lot of attention heads, and we're definitely not going to do a grid search over all of those alphas. So here we're going to try and learn alpha and let the model learn that. And so what we contribute is a closed form expression for the gradient of alpha and max with respect to alpha. Note that this is not trivial. It requires something called argmin differentiation. And if you want more mathematical details, you should check the paper. If you don't care about the mathematical details, you can just do pip install antmax, and it will work right away with normal gradient descent in the middle of your nodal as the normalizing function. So we tried this on several machine translations data sets of different sizes and different language pairs. And we compared this model with a normal transformer with softmax, and also with a model with using 1.5 antmax in all of those attention heads. And so this model of 1.5 antmax, it has constant sparsity propensity in all of those attention heads. And in the alpha antmax model, this normalizing function is able to learn how sparse it wants to be. And what we found is that we have comparable results to softmax. And in all of these cases, we actually have a small boost in performance. But what we're really interested in is analyzing these heads. We're going to do this for the language pair of English-German, data set of WMT14, which was the largest data set that we used. But if you want to check these analyses that I'm going to do for other language pairs, you can check Appendix A of our paper. So the first thing that we asked ourselves is, how do these alphas that control the propensity for sparsity distribute themselves over the several heads of the model? And what we found is that the encoder self-attention, we have a bimodal distribution. And so we have a mode that is between 1 and 1.5. Recall that every alpha that is greater than 1 can still have a sparse distribution. It's just that the propensity for sparsity increases with alpha. And interestingly, in the encoder self-attention, we have this little mode that is very, very sparse with alpha close to 2. In the case of context attention and the decoder self-attention, this is mostly unimodal, between 1 and 1.5. The next thing that we asked ourselves is, how do these alphas vary throughout training? And we randomly initialized the several alphas in the model, and you see that they converge to different places. But what is really interesting here, in my opinion, is that some of these heads choose to be dense in the beginning of training, and then they converge to a sparser probabilities. So what we hypothesize this means is that in the beginning of training, the model is not so certain of its decisions, and it decides to be more dense, so to be more general. And as training progresses, the heads get more certain about their roles, and it becomes more sparse. And so now we asked ourselves about the specialization of these heads. And to do this, we measured the Jensen-Shannon divergence between the several heads, the several probability distributions in the several heads in the same layer. And what we found is that this divergence is higher for our sparse transformer models for most of these layers. And what this means is that for the case of softmax, the heads are more redundant. They are looking at the same places and in the input representations. Whereas in our sparse transformer models, they have more diversity, and so they look at different places. They are more specialized. And as seen in an earlier paper this year by Elena Wojta at ACL 2019, specialized heads are really important to the output that you get in your model. So then we decided to look at some concrete examples of head roles. And this is also something that was seen in the paper that I just mentioned of ACL 2019, which is a positional head that looks at the previous token in the sentence, in the sequence at each time step. And as you can see, softmax is completely dense. So it is true that its highest weight is being given to the previous token in the sequence, but it still gives some amount of probability to every other token in the sequence. Whereas in our sparse transformer models, it only looks at the previous token. And in the case of the alpha and max, it learned to be very, very sparse for this specific head role. So it has a much crisper attention. Another thing that we were interesting to notice is that some heads learn to be dense because density also helps the model. In this case, we found an interrogation detecting head. And what this does is that in the time step of an interrogative word, like what, it places its highest attention weight in the question mark at the end. And in this case, actually 1.5 Ntmax, the one in the middle here, is the one that is worse at doing this specific task, this head roll. So it seems that for this specific task, it is very beneficial for this particular head to be dense. And so alpha Ntmax decided to have a very small alpha, closer to softmax. Another curious thing that we found is that some heads emerge that are not found in the softmax model at all. This is one case of that, where the head looks at its own position at each time step, except in subword tokens. In the subword tokens, it decides to split its attention over the several subwords of the cluster, making a representation of that complete word. This was something that we did not found in the softmax model according to our metrics. So maybe this happens somewhere in the softmax model, but since everything is dense and the heads are very entangled, you can't really find these kind of roles. Whereas in our sparse models, the heads tend to be more diverse and you can disentangle these head roles. So the key takeaways here is that we introduced this adaptive sparsity that we use for transformers, but this can be used for anything that uses a normalizing function, like softmax. We use this via alpha and max with an alpha parameter that is gradient learnable. This leads in our transformer, it leads to adaptive sparsity for each head. The head redundancy of the heads in each layer is reduced. And we get clearer head rolls. Thank you for your attention, and I'm happy to take any questions.
So we have a time for 1 or 2 questions. I want to ask a question about the motivation of this work. Why do you want sparsity in these attentions, not that there are some dense attentions anyway?
The motivation here is to use sparsity to better interpret the attention in the models, because in dense distributions, even if it's multiplied by a very small probability, the output will be affected by it. And in this case, you will have actually absolutely zero probability multiplied by some input representation. So your output will only be affected by some of the inputs.
Hi, nice work.
Hi.
Is there a way with your technique to also get group sparsity?
Sorry, could you repeat your question?
Yeah. Is there a way with your techniques to also get group sparsity, that is to get nullify like a full layer or something like that?
I think, yeah, that would be pretty interesting. So in this case, we use a different alpha for every different head in each of the layers, in each of the attentions. But you could definitely choose an alpha for just the same layer or group of heads, and parameterize that alpha only for that group.
Okay, so let's answer speaker again.